So we are Team SAKA and we'll be demonstrating a solution for the AI problem statement that we have proposed a deliverable for. We'll move on to the coding system. So herein we have started 3 terminals. The first one is for the Flask server, the second one is for frontend, and the third one is for running the Kafka and the Zookeeper containers. We have provided the setup descriptions within the README file as well. So we'll go on to our mockup UI that's there. This is for the POC. You will upload your CSV over here. You can integrate this with API calls in the production as well. You can keep track of what's being uploaded over here since we are conversing with the Kafka queues, so it allows us to keep track of systems. And the entire knowledge graph is traversed for each product that is inserted, as you can see within the logs. And calls are made to Grok API as well. So that is the Llama 3.2 vision model, so that we can incorporate and extract features from the product descriptions and images, etc. So we'll see how the system is working. We'll go on to the architecture. Basically, user uploads his or her CSV and that goes to the front-end application. It's sent to the Kafka for scalability considerations, obviously. Like when we are initial knowledge graph construction would require millions of products. So traversing to all that and manually uploading is kind of tedious. You would need some asynchronity in order to keep the loose coupling between front-end and back-end services. And we have incorporated that over here. We have used a vector score, the proposed basically, so that user feedbacks can be incorporated and sent to LLM for better feature extractions in the future cycles. This data is sent to LLM by we can basically filter some parameters if required, and LLM responds with 4 primary classes with the help of output parsers, which are namely apparel, footwear, accessories, and home decor. These pillars actually incorporate, if not all, most of the fashion products within the ecosystem, allowing us to create an extensible ontology. And later, these are mapped to Cypher SQL queries for the knowledge graph creation. This is built for a horizontal scaling, making it adaptable for most deployment scenarios. We have incorporated temporal dynamics as well. In brief, basically, you can use agents or data scraping utilities in order to actually fetch the data for real-time trends that are going on. One example could be of using fashion dictionaries, whose link we have provided over here. So by visiting that later, you can check as to what's the current status. And basically, these are updated periodically, so live data can be fetched. So moving on, and backfilling strategies are also incorporated, so that basically LLM generates classes that the four we discussed earlier. Those are stored. You can store that within a data store, let's say MongoDB. These classes represent concepts and thus are unique. So basically, it allows you can periodically run serverless scripts to traverse these and name and change the terminology namings depending upon the convention. Like comfort wear could change to athleisure within some years of time, or some other concepts. Those backfilling strategies for creating different versions of knowledge graphs can be incorporated. And this is computationally lightweight. Also, this makes it adaptable for big data as well, rather than using knowledge graph embeddings and reconstructing everything, which is kind of not good for consistency. And this is the exhaustive pipeline. You can definitely go through this. In extensibility mechanisms, as I discussed, the sample class given below has an let's say has an attribute. So the classes have attributes, and those basically they define the firmament and they give consistency. While the fields of those are filled by LLMs. So basically, LLM acts like an object factory. It spawns instances which are adaptable with time, allowing us to create a consistent yet transient knowledge graph. Moving on to the multimodal LLM for feature extraction, we have proposed that it would be better to use a single LLM rather than using multiple models, one for feature extraction and other for making the ontology dynamic in some way. It is whose reasons are specified over here. In GIST, basically, computer vision models would be naturally leading to transformers for describing the images. If you define the terminologies, basically you're stuck to a time step. So like there is no temporal fluidity. And moving on to the architecture of the model itself, the unifashion LLM outperforms all existing models, as suggested in the research paper that we provided in ideation as well. We use the Lava vision model for the base, and due to quota constraint, basically we weren't able to use 8-bit quantization. You could get better results by that. We have used 4-bit quantization for now. Also, we have provided the link to LoRa parameters that were used to fine-tune the model. And as a suggestion, we would highly recommend you to refer continual Lava for more sophisticated way to fine-tune the model continuously for production, even though we have suggested the vector store for which stores the user comments. That being said, I will just give a brief demo. Actually ran this notebook earlier, but it's kind of taking too much long to execute. I'll just go through what the steps that I took over here. So like initially I installed the dependencies. Moreover, like we downloaded the snapshot of the model, and you can see that the files have been downloaded. Over here we loaded the model, which was the base Lava. And then we just took a sample example of the image of a national park, and you can see that the image description was quite accurate. Then in order to transfer the learnings of the Unifashion LLM parameters using the LoRa adaptation, we cloned the Unifashion repository on GitHub, Hugging Face, and thereafter, after loading those parameters, we took a sample example, it was from the t-shirts CSV that was provided by you. Moreover, we added some instructions for the model. And this was the thing. So for this particular example, you can view the description. It has quite intricately described that it was a black t-shirt. It had the accents that it had. Moreover, the specific pattern, also its occasion, casual and stylish. Fabric, if the fabric metadata had been provided, which is being provided in the metadata, it will be able to do that as well. The stitching and then the neck type, which was collar, moreover, and whether it's okay, and basically which adds somewhat semi-formalish look. and you can see that it was also wearing brown belt, which complements the shirt. So what's happening is that it's kind of understanding and relating the two cloth items as well. So one can actually incorporate the pairs well with, as well as trend nodes, which we'll be describing or discussing further. So what is happening is the domain levels are given over here. This is the schema. So like domain level is the fashion node, the root node. Then we have categories of apparel, etc. And then subcategories we have moreover occasion level specifications, and then item and product level, wherein we actually arrive at a more primary function or form of the fashion entity. And the lowest layer is of is a more like an adaptable or fluid layer, we can say, wherein you can have attribute level classifications, contextual level as well, introduce dynamic trends as well. So like if you which product goes well with which product. So like what pairs are going on, and other than that, also in future scope you can incorporate trend nodes, which can basically allow more like visually appealing relations between different categories or different trees within the knowledge graph, which schema basically is available on the next page if you would go there.
Yes, okay. So just a second. Yes, okay. So as you can see, status success and data has been sent to Kafka. File has been uploaded successfully. So when I go to Neo4j Aura and okay, I'll run this query again. Okay, so you can see this ontology has been created. This is the root node, the fashion nodes like we discussed right now. It is divided into 4 categories: footwear. The second one is apparel, accessories, and the last one is home decor. We'll move to apparel, which is the widest category we have. For example, if you see over here, apparel, it has various categories like western wear, winter wear, fusion wear, athleisure, and traditional wear. Uh, Let us directly, as you can see, these are subnodes which have their own attributes. For example, jeans can be bootcut, straight, or skinny. Shirts can be half sleeved or collared or full sleeved or slim fit. We'll move to a very interesting part over here, a very interesting phenomenon that has occurred when we are creating this ontology. When you come into the fusion wear domain, and you have two parts like in fusion wear you have tunics and in traditionals you have lehengas, but they have same attributes. The attributes have overlap, which are embroidered and printed attributes. You can see over here that there is a very beautiful cross category mapping. You can see that tunics has been mapped to printed and printed is mapped to lehengas. This is a very good example of cross category mapping. Coming to the last part, for example, okay, we'll come here. Trend mapping. Saris is the center node, and saris pair well with gold necklace and earrings. So that is why this is a trend node which we have added. You can see multiple trend nodes over here. For example, wrap dresses pair well with stilettos and handbags. There are a lot of trend nodes over here. I'll only explain a few. For example, Kolhapuri chappals, which are very popular in Maharashtra, pair well with dhoti pants and kurtas because they are traditional wear. We have added a very detailed video in a presentation regarding yes, this one. We have added a very detailed video in a presentation regarding the ontology. The ontology is very huge, and we could not take a screenshot of it. That is why.
As discussed about the pairs, and the dynamic trend nodes could be further extended for basically incorporating multiple features that arrive within the future. So like more like generic terms could be used to link, such as like let's say wristbands and accessories could be paired with polyester shirts or something that are present in the apparel category. So like, and they could all be combined within the trend of like sportswear or something like that. So those things can be incorporated as well. Moving on, this we talked about this right now, and some basically individual product level attributes that could be incorporated for the future use cases.
Yes, okay. An example of that is maximum retail price. Because Stylumia is an analysis focused company, client analysis focused to be more specific. You have multiple clients, like let us consider client X and client Y. Client X and client Y have manufactured a shirt which is of almost the same material, the pattern is almost the same, but the company X comes to Stylumia to tell that this product is not selling to an extent to which it must have been sold in the market. So Stylumia can very intelligently come into our ontology, which is displayed over here. It can actually click on the shirt, which will be a product node, and then it can check that the MRP of the product X is higher than that of the product Y, and that is why the sale is not up to the mark. Also, we have included URL, which was also available in your given dataset. URL actually allowed us to do a lot of web scraping, and we can actually directly redirect from the knowledge graph through this URL. Recommended pairing is the blue colored nodes which we saw in the knowledge graph. Why did we choose Neo4j over OWL? So the main reason was that Neo4js allowed us to use CSV files APIs very smoothly. There were no errors and such that OWL is actually a logical reasoning focused ontology building system. It was not able to store the various nodes and everything like Neo4j used to store. Also, Neo4j has a beautiful collaboration with Python. We could actually automate the process of converting the 100K dataset into nodes directly through Anaconda Navigator and all that. Yes, so this is a snapshot of the entire ontology which we saw. We also, yes, so this is the ontology when we uploaded the CSV file.
And yeah, we have been able to incorporate new trend mechanisms as well. Like pairs well with features for capturing what products go well, like are generally paired together. So for in order to understand what are general fashion preferences, and advanced fashion preferences will come within the trend nodes as well. First and going on. So yeah, we have kind of wrote a lot upon version and update methodologies as well, as to how like after backfilling strategies and all, how different versions would be created, and basically comparison between those would occur. and some development scenarios as well. Along with that, feature taxonomy overviews and some additional notes, like some like specifying cross-category relationships, then advanced feature designs, and what we are currently working on.
So,
Yeah.
okay, so basically, like, we are also trying to improve this project. We are trying to add project-specific nodes. For example, we will add 100 models of Kolhapuri chappals in the parameters of the Kolhapuri chappals node, and basically, all of them will have unique attributes. For example, purple mojalis or purple Kolhapuri chappals will pair very well with purple colored kurtas, and we will have a product-to-product based node, which will be more end-to-end solution and it will be more apt for the market. That is the that will be the USP of our project because there is no current solution available in that domain. It will really be a state-of-the-art solution. It will also be able to forecast trends. Like for example, there is some blue sari coming from XYZ company, and there is a blue colored bracelet for from some other company. Let us consider YZ company. So they will go very well together, and Stylumia can also tell the both companies to collaborate or do something like that however they wish. But yes, that is a very important point.
Yeah, and some of the nodes that we did prefer some other models or considered them, like encoder-based models like Robert and this, but they mostly are encoder-based families and not would not be able to adapt to the complexities that arrive as well as. And Unifashion LLM was by researching the research papers actually that was the one that's best performing, and we would highly recommend you to check the LoRa parameters that we have proposed for it. So yeah.
Yes, okay. So we come to the end of our presentation over here. You can see the software is working really well. Neo4j is being updated after the addition of every product, and we are also displaying the CSV files row over here. Grok API is providing us the Meta LLM, Meta Llama LLM, and the response also you can see over here that the structure response it is under that category and everything like that. So we come to the end of our demo, and thank you.